Welcome back. This lesson we're going to be looking at factorizing polynomials. So let's just take, for example, a cubic function, and if we could express it as three linear factors, so let's just say we had x plus 2, x minus 3, and x plus 5. When we expand it out, we know that the final term would be 2 times negative 3, negative 6 times 5 would be negative 30. We would have x cubed and then some other junk in here. Now, if we're trying to find these factors, let's say we've given out the full expanded form and we had to try and get to this. This was what the answer we're looking for. We could do a long division if we knew one of these factors, but how do we get there the first time? If we look at the constant term at the end, the only way that can come about is from the terms without the x's multiplying each other. So we look at the factors of 30 and we try and sub them in. Now, into the function. Now, if one of those was correct, so this is f of x, if I was to sub in into this bracket here, negative 2, that bracket would become 0, and then I'd have the first bracket is 0, and it doesn't matter what any of the other two brackets or factors are, anything times 0 is going to be 0. So if x plus 2 is a factor of a polynomial, then f of negative 2 must equal 0. And likewise, if x minus 3 is a factor, then if x were to equal 3, the whole thing must be 0. So if I subbed in 3 for x, I should get 0. And you can see the pattern here. F of negative 5 must also be 0. So if we can recognize that and that pattern there, if we didn't know the fully expanded form, we could substitute in values to try and find when the function equaled 0, and we'd look at that x value and we'll try and set up one linear factor based around it. So for example, if we found f of 1 equaled 0, then x minus 1 must be a factor. And we get what's called the factor theorem. So generic factor, let's say x, we can even go even further and change the coefficient of x, aren't we? Ax plus b, if f of negative b on a equals 0, then ax plus b is a factor. So we need to find what the value is that we sub in for x to make the whole thing 0 before we even begin. So let's look at one example here. We've got a cubic function, x cubed plus 3x squared plus 3x plus 1, and we have to factorize it. Now, we don't know, is it going to come down to one linear factor and quadratic, or will it come down to three linear factors? So we need to try and find a value for x. Now I could start just subbing in values for x and finding out what equals 0, but if I just subbed in any number and guessed, there's an infinite amount of choices, possibilities. So I look at the last term, coefficient, go, it's 1. So I'm only looking for factors of positive 1. And that could be positive 1 or negative 1. So I'm going to substitute in both and see if one of them is a factor. So let's sub that into our function. First of all, I'll do negative 1. We'd have negative 1 cubed plus 3 times negative 1 squared plus 3 times negative 1 plus 1. And we get negative 1 plus 3 minus 3 plus 1. Negative 1 plus 1 is 0, plus 3 minus 3 is 0. So that's great news for us because that tells us, therefore, x plus 1 is a factor. Now, I could take this and do a long division to find the remaining quadratic and then try and factorize that. But while we're here, let's just check positive 1 to see if it works. So we go 1 into all this, 1 cubed plus 3 times 1 squared plus 3 times 1 plus 1. I'm going to get 1 plus 3 plus 3 plus 1. And I can get to here and go, not going to equal 0 if I wanted to. Alright, or it equals 8. Now, as a side note, if we were to do a division, that would actually be the remainder if I divided f of x, which is this original cubic here, by x minus 1. If I divided them through, I should get a remainder of positive 8. That's the remainder theorem, but for now, that's no good to us. So let's look at this first one. We've got x plus 1 is factor, so we can do our long division. So x cubed plus 3x squared plus 3x plus 1, all divided by x plus 1. Let's use the synthetic method. So the value of negative 1 would make the denominator 0 here, so that goes in my box. At the top, I use the coefficients. There's nothing there, it's all 1, 3, 3, 1. And then I put a 0 here, always a 0 in that box, and I add the top and middle rows to get the bottom row. So 1 plus 0 is 1, and then I take my negative 1 that's in the box here, multiply it by this new answer 1, and that gives me this value up here. So negative 1 times 1 is negative 1, 3 plus negative 1 is 2, negative 1 times 2 now comes up here to give me negative 2, add them would give me 1, negative 1 times 1 is negative 1, add them, get 0, and that's our remainder. And if you're not getting a remainder of 0 there, you know you've made a mistake somewhere, because we already know that it should be a factor, so we shouldn't have any leftovers. And we can see our coefficients. So now that means that all of this is equal to one lot of x squared plus 2 lots of x plus 1. And when we write that all out, we can say therefore x cubed plus 3x squared plus 3x plus 1 is equal to, now because I've done the division, I know this quadratic, but I can't leave off this factor here. So that's just saying this whole thing here is equal to x plus 1, which we found from using our factor theorem over here, multiplied by the answer to our long division over here, x squared plus 2x plus 1. And you should recognize that quadratic. We can factorize that further. X plus 1 multiplied by, we're trying to factorize this quadratic, we're looking for factors of 1 that add up to positive 2. So it'd be x plus 1, x plus 1. Yeah, hang on. Nice and easily. We've got x plus 1 all cubed. So that's a fully factorized form.